All right, welcome folks. So in this experiment 2 of lab number 8, we wanted to build the circuit shown here, and in this circuit we wanted to validate that KCL, KVL, and Ohm's law are still valid in the time domain. So when we apply a time domain signal, the signal will be valid. So that's our objective in the second experiment. So, and to build the circuit, what we did is I came into the breadboard and I built the circuit. So let me move to the breadboard to show you how does the circuit look like. So here is the circuit on the breadboard. Let me bring it a little bit closer to you. It's very much similar to the circuit diagram you have. So one of the things we explained that when you build a circuit on the breadboard is to make it very similar to the circuit diagram. This is R1, this is R2, R3, and R4. This is the ground node, this is the input, and that's the ground. So it's basically the same circuit. Basically it's the same circuit that we have in the circuit diagram. So, and then in step 1 it says that let's measure the resistor values. When I measured the resistor values, I got R1 was 2.155 kilo ohm and R2 was 4.625 kilo ohm. R3 was 0.9895 kilo ohm and R4 was 9.747 kilo ohm. They are very close to the nominal values within the 5% tolerance that we said. So let me zoom out a little bit to show you how we're going to build the circuit and connect the oscilloscope and the function generator, which assembles steps 2 through step 5. So I'm going to zoom out, as you can see. So here I am. Let me bring the circuit board a little bit closer so you can see it. Here is the circuit board. I have it over here. So in step number 2, it says that using the BNC to BNC cable, connect and the T-splitter, connect the BNC to BNC cable to the scope to channel 1. That's something we already have. And let's configure the signal to be a sine wave. So I'm going to click on sine wave, and I want it to be 10 volts peak to peak at 10 kilohertz. So I'm going to do, I don't need brush here. So what I'm going to do is I'm going to do 10 volts peak to peak. So the amplitude going to be at 10 volts peak to peak, and then the frequency I'm going to program it to be at 120 hertz. 120 hertz. So that's what I have, 120 hertz. So that was step number 2. Then I'm going to use a PNC to alligator cable. So here is a coaxial. Those are called coaxial cables, but it's going to have a PNC to alligator. PNC to alligator. So I'm going to connect the PNC to the function generator, and the alligator will go down to the circuit. So the red will be the input. The red line is the input. So this is my input cable or jumper, and this here is my ground, my 0. So now is we have sent this signal that we measure on the scope to the circuit, and that was step number 3. In step number 4 it says that to measure the nodal voltages, I'm interested in node V2 and node V4. The Vs, which is the signal voltage, is the signal that will measure channel 1, which is basically this BNC cable goes to channel 1. So now I'm gonna use the probes. So here is the probe. This is probe is then an instrument used to probe, to measure the signals. So this is the probe, and the probe will have a button. This probe will have a button where it can say that it's 10x or 1x. I'm gonna make it a 10x, so I can move it to 1x, 10x. So this probe, you can adjust it to 1x and 10x. So the 10x says that we're gonna divide the major signal here by 10. That means I have to set the scope to multiply by 10. So this divides by 10, this multiplies by 10. The reason is that when we divide by 10, it is configured such as it will give us a higher bandwidth. Means that we're going to measure higher frequencies. Means that the equivalent capacitance of the probe going to be smaller. It gives us higher frequency. It's a little bit advanced topic, but the problem with the 10x is you can't measure very small signal. So the disadvantage is you can't measure small signal, but you will be able to measure higher frequency. So here we're going to use the 10x probe to measure the signal. So remember that probes are always used to measure signals. So I'm going to use channel 2 to measure the node V2. In fact, let me use a jumper. It's good practice to use jumpers. So I'm going to use a jumper for node 2. And I'm going to measure the second voltage. So I'm going to use another jumper to measure the V4 at node 4. So here I'm going to use channel 3 to measure the signal. Here I have a ground. So what happened is once one connector, one of those channels is grounded, all the channels are going to have the same ground. But I'm going to do it here as a form of redundancy. I don't need to do that. Once you ground one channel, all of them are going to have the same ground as this channel. So this channel is already grounded. So this and this channel, this channel, this channel, and this channel have the same ground. Basically what the probe will do is it will measure the voltage in reference to ground. Now what I'm going to do is I need to configure, make sure that I configure the scope to give me channel 10. So I'm going to move into the scope. Let me move into the scope a little bit more so I can show you how to configure the channels. So channel 1, I'm going to click on it. Here it says that the probe is 1x. So this is a wire. It doesn't divide by 10. Whatever you send is what you receive. The BNC to BNC. So it should be 1x. So the BNC to BNC is 1x because there is no division. There is no electronic circuitries to divide. However, if you're going to use those probes, the probes have electronic circuitries, gotta divide by 10. I set them to be 10x. That means the probe divides by 10. That means the scope need to multiply by 10. So what I'm going to do here is I'm going to click on the blue button. I want to make sure that's 10x. It is 10x here. And I'm going to click on the red button. I also want to make sure it's 10x. You see how it shows it's 1x? So I'm going to click on this one here. It's navigating through the menu basically. And then here where it says attenuates, it attenuates means to reduce by a factor of 1. I want to make it attenuate by a factor of 10. So I click on it one more time, and now it's attenuating by a factor of 10. Now I'm going to do auto set, and let's see what we have when we do the auto set. You're going to see 3 signals on the screen that will show you that shortly. Now when you want to measure signals, you don't want it to leave it at the auto set. The auto set will show you the shape of the signal, but you really want it to measure the signals. So you need to zoom in to get more accurate readings. So I'm going to zoom in with this one. So I make it bigger, which is channel 1. And I'm going to bring it down to the center. So I'm going to overlap all those 3 signals together. Same thing with channel 2. You want to make sure that's not clipping. If it's clipping outside the screen, you're going to get the wrong measurements. And then I'm going to do the same thing with channel 3. And I overlap the zeros all at the same time. I'm going to zoom in one more in the time scale. I'll get a better reading, as you can see. So I'm navigating the scope to get better readings. Now what I'm going to do is I'm going to click on measure. So let me zoom out a little bit to see the different buttons I'm using. Here you go. So I'm going to click on measure. And instead of using my eyeball, which I can do that, I can basically decide that I wanted to measure the signals using the measured menu. Here is my measured menu. The first one says that it's going to measure channel 1, peak to peak value. That's what I need, which it shows that it's 10 volts. And then channel 2, it shows the frequency, which is around 120 hertz, fluctuates a little bit. Channel 2 shows you the peak to peak value of channel 2, and that basically your V2. And channel 3, it reads the max. I don't want the max, I want to change it to peak to peak. So I'm gonna come in, click on this one. Now it says that the source is channel 3. I'm measuring that channel 3. The type is max. I don't want max, I want peak to peak. So here is time rise, time fall. I keep clicking on it. Position the positive pulse width, negative pulse width, none, frequency, period, mean, that average, peak to peak. That's what I want. So I click on measure again. And now I'm showing all the measured values. At this point, we're going to rely on the measurements that we have instead of using our eyeball. So let's record those measurements. That's basically step number 6. So VS in here shows that it's 10 volts. So one way to measure accurate values is to use stop, so things doesn't fluctuate at this point. So VS will be 10 volts. And then we're going to have V2 going to be 6 volts. And V4 going to be 5.56 volts. So those are based on the measurements that I have here. I recorded those values. Now what I wanted to do is, in step number 7, from those values I can estimate what's the voltage across R1 is, which is V1, what's the voltage across R3 is, which is V3, basically using KVL and to do that. And then I will be able to use Ohm's law to determine what's I1, the current through R1, the current through R2, the current through R3, and the current through R4. So that basically, based on those measurements, I can do step number 7 to estimate those values. Step number 8 says validate KCL. In this part of the experiment now, we're going to use the DMM, the digital multimeter, to measure the voltage and currents of the circuit when it's a sine wave at 120 hertz. So we wanted to see what's the advantages of using the DMM and what's the disadvantages of using the DMM over the oscilloscope. So here we're going to use the DMM. So this is the positive voltage, the red is the positive voltage, and or the positive end of the measurement, the red. The black line going to be the negative end of the terminal. So the first thing I'm going to do is I'm going to measure the voltage across VS. So this is VS. That's basically the voltage comes into the function generator. This is the ground, so I'm going to connect this to ground. And let's see how much we get. So I get 3.502 volts. 3.502 volts, that's my measured value. It's fluctuating, 3.50102. I recorded it as 3.502 volts. That's what I have here. I'm going to measure the voltage across R1. So the voltage across R1 is going to be this voltage here, which is the voltage across this resistor, right? And this is going to be 1.3996. So I will write it as 1.3996 volts. Now keep in mind that the DMM measured the voltages in RMS value. Those are in RMS value. To get the peak value, you multiply by square root of 2. Right? It's an RMS value, and this is a sine wave. To get the peak value, you multiply by square root of 2. To get the peak to peak value, which is the value we measure from the oscilloscope, you're going to multiply by 2 times square root of 2. Right? 2 times square root of 2 times the RMS value will give you the peak-to-peak value, because you wanted to compare the RMS value measured from the DMM to the peak-to-peak value measured from the oscilloscope. That's our objective over here. So now we're going to move to the voltage across R2. So R2 will start from this node over here. It's to ground, right? So this is R2 over here. So we're going to measure it to ground. And what I have is 2.100, I would say 0.2. So if I move closer to the circuit, I have electrostatic voltage, electrostatic field, right? That will basically affect the reading. I would say roughly 2.1 volts. That's a good value. So 2.1 volts, that's what we have here for the voltage across R2. Now I'm going to measure the voltage across R3. The voltage across R3 comes from the top node to the side. This is your R3 here. So I will have 1.937. I can route it to 1.938 millivolt. Or I can say 0.1938 volt. That's what I'm going to write, 0.1938 volt. Now I'm interested in the voltage across R4. So R4 is the last resistor here, will come from the top node, V4 to ground. So it's basically V4. And I will have 1.9055 volts. 1.9055 volts. That's what I have. And keep in mind that this is an RMS value. You still want to convert it to peak to peak. You multiply by 2 times square root of 2. So this is basically to measure the voltage. Now we wanted to measure the currents. So how do we measure the currents? First of all, we need to configure this to be currents. So I'm going to disconnect those 2 cables here for now. It's disconnected. Then to measure the current, the red going to be here. And the red is where the current enters, and the black cable or connector where the current leaves. And then to measure the current, you're going to click on AC current. We measure an AC current here, and you have to break the circuit to measure the currents. So I'm interested in I1. I1 is the current going through this resistor. So I'm going to break R1. Here I break R1. And then the current will come in from the node, from the beginning of the circuit, and it will go to the resistor. That's how we measure the current. So here we have 0.646 milliamp. 0.646 milliamp. Right? So less than 1 milliamp for the total current comes from the circuit. That's how I measure the current. Now I'm going to bring the resistor back, so I need to disconnect the amp meter, and I'm going to connect the resistor back to the circuit. And now I'm going to measure the current going through R2. So I'm going to break R2. So here is R2. I will break R2. R2 is broken. And then the positive current will come from the top node to the resistor. From the top node to the resistor. Now keep in mind that this current is an RMS value, and the RMS value doesn't tell you if the current is positive or negative. It's just going to give you the value. It doesn't matter if you flip the polarities. I will do that once we record this value to show you that you're still going to get a positive value. So here we have 0.452 milliamp. Keep in mind that this is RMS value. To get the peak-to-peak current, you still need to multiply by 2 times square root of 2. I'm going to flip the direction of the current. See, still positive. And the reason is RMS will tell you what's the effective average value. What's the RMS is? It's what's the equivalent DC value to that current. Because a sine wave goes up and down, right? So it's going to be positive and negative. So what's the RMS value means? It's the equivalent DC current. The equivalent DC current. That's what the RMS value means. It's actually, you square the sine wave so it becomes positive. You take the average of the squared sine wave, it's a positive value, then you take the square root of it. So it's always a positive value. RMS value, always a positive value. So now what I'm going to do is I'm going to connect R2 back into the circuit, and then I will measure R3. I will measure the current through R3. So I'm going to disconnect R3 from the circuit. Here is R3 is disconnected from the circuit. The current will come from the top node to the resistor. And here I will have 0.19556, I would say 0.195 milliamp. So here I'm recording the values for step number 11. So it's in milliamp. Then I'm going to disconnect the amp meter. I will connect the resistor back again into the circuit. Now remember that we've been doing those kind of measurements, current measurements using DMM all the way through the semester. So it shouldn't be a problem at this point to know how to measure the current through each element. You always break up the resistor or the element, and then you connect the amp meter in series with it. So finally for I4, it should be the same current as I3 because they are in series. But now I'm going to connect the amp meter in series, and I have 0.195 milliamp, the same as I3. So here I was able to measure the AC voltages using the DMM and the AC currents using the DMM. Now the DMM will give us easy reading. It's very easy to measure the values, as you can see, compared to the scope. It's easy to measure the current compared to the scope. Scopes measure voltages at the nodes. You can do current measurements with the scopes, but basically you need expensive probes. The disadvantage of the DMM is that the DMM doesn't show you the shape of the signal. It just gives you RMS value. So the signal can be distorted. It can be a triangular pulse. I wouldn't know what kind of signal do I have. To know the kind of signal you have to use the oscilloscope. So the oscilloscope have the advantage of showing you the signal. Then you can look at the fidelity or the quality of the signal. Is the signal good? Is it noisy signal? Is it a pure sine wave signal? You can determine that using the scope. So I would say that the scope is more powerful than the DMM. Another thing about the DMMs, at super high frequencies you can't use DMMs anymore. The DMM have to convert that major signal into an analog signal, so it has to use A to D converters, and that will have limits on the frequency of the DMMs. The scope will show you the shape of the signal, so that becomes advantageous compared to the DMM, because the DMM will only show you numbers, will not show you the quality of the signal. So the remaining steps in the lab basically gonna talk about validating KCL and validating KVL and list the pros and the cons of the DMM, and that should be the end of the lab. I hope you like this lab. This is a very good and practical lab, and good luck to you.